Today I'll be talking about radical axes. And you guys can see my screen, right?
I see a blank white screen, so if that's what it is, then yes.
Okay, thanks. Okay, so to start off, so you've probably heard of power of a point. So I'll start off with the definition. So if you have a circle, omega with center O and a point P, and you were in the same plane, then the power of P with respect to omega is OP squared minus R squared, where R is the radius of the circle. And you can see that this is basically like the definition that you're probably used to, since this is basically OP plus R, and this is OP minus R. So they multiply to OP squared minus R squared. Yeah. So basically, if P is inside the circle, then you can see that this quantity is negative, and if P is outside the circle, then this quantity is positive. And if P is on the circle, then it's equal to 0. And now I'll introduce the radical axis. So if you have two circles, and their centers are distinct from each other, so basically the circles are not concentric, then the radical axis of the two circles is the set of all the points in the plane such that the power of the point with respect to each circle is equal. So if you let this circle be omega 1 and this circle be omega 2, and you consider any point P, then you can write this as the power of P with respect to omega 1 is equal to the power of P with respect to omega 2. And the radical axis is basically a line that's perpendicular to the line connecting the center of these two circles. So in this case, where these two circles intersect at 2 points, you can see that the radical axis is a line that passes through the 2 points of intersection of these two circles. And to prove this, you can basically chord bash. So if you let the center of omega 1 be 0, 0, and the center of omega 2 be a comma 0, where a is a constant, then the power of the point x comma y is basically with respect to omega 1 is x squared plus y squared minus r1 squared, where r1 is the radius of omega 1. And if you set this equal to the power of the point with respect to omega 2, and then you can write that this is equal to this quantity. And this is because it's basically from the equation of the circle. I think I put the handout on the Google Classroom. So let me know if you can't access the handout. Okay, so if you simplify this equation and solve for x, since the x squared and y squared terms cancel out, you'll be left with x is equal to a squared plus r1 squared minus r2 squared over 2a. And this is basically the equation of a line that's perpendicular to the x-axis, which is basically what we wanted to show. Okay, so now I'll introduce the radical center. So if you extend this to 3 circles, basically the pairwise radical axes of the 3 circles all pass through one point. And another way to say this is if you have 2 circles, omega 1 and omega 2, and you have points A and B lying on omega 1 and C and D lying on omega 2, then the condition that A, B, and C, D intersect on the radical axis of omega 1 and omega 2, this is equivalent to A, B, C, and D lying on a circle. And as long as this, the center of the circle is not collinear with the circumcenters of omega 1 and omega 2. And the reason that we have to have this condition is that if they are collinear, then the radical axes can't intersect since they are parallel to each other. So to prove this, so basically we need to prove 2 directions. So if you let A, B, and C, D intersect at a point P, then first we can show that if P lies on the radical axis of omega 1 and omega 2, then A, B, C, D is cyclic. And P lying on the radical axis of omega 1 and omega 2 basically implies that the power of P with respect to omega 1 is equal to the power of P with respect to omega 2. And this, from this you can write that PA times PB equals PC times PD. And this basically is enough to show that A, B, C, and D are concyclic, are the converse of power of a point. And now we want to show that if A, B, C, D line a circle, then A, B, and C, D intersect on the radical axis of the 2 circles. Okay, so to do this, again, we'll let P be where A, B, and C, D intersect. Then you can see that basically the radical axis of the circle of A, B, C, D and omega 1 is AB. And similarly for omega 2 and the circumcircle of A, B, C, D. So you can express this using power of a point. And this basically shows that the power of p with respect to omega 1 and the power of p with respect to omega 2 are equal. So this means that p has to lie on the radical axis of omega 1 and omega 2. Okay, so I guess we can go into the first example. So we want to prove that the three altitudes of a triangle all intersect at one point. Okay, so let's call this triangle ABC. And we'll let the feet of the altitudes from A, B, and C be D, E, and F. And basically we want to show that A, D, B, E, and CF all go through the ortho center. Okay, so we know from before that if you have the three pairwise radical axes of three circles, then the lines all intersect at one point. So we want to maybe take advantage of that for this. So what we want to do is find three circles whose pairwise radical axes are A, D, B, E, and CF. Okay, so basically you can see that A, F, D, E, D, C is cyclic since angle AFC and angle ADC are both 90 degrees. And similarly, you can show that BFEC and AEDB are cyclic. So you can see that the radical axes of the three circles are A, D, B, E, and CF, since they're all chords of two circles. So from the radical center theorem, you can see that they all intersect at one point, which is the ortho center. Okay, so this problem, I don't think it was on the handout, but another interesting example is proving that the circumcenter of a triangle exists. And you can think of this as there exists a point such that the distance from that point to each of the vertices of the triangle is the same. Okay, so this is basically where the idea of having circles of radius 0 comes in. And this can actually be applied to like a lot of different problems. And yeah, so if you call this triangle ABC, then you can think of basically having circles of radius 0 at A, B, and C. Then you can think of basically drawing the radical axis of the circle at A, B, B, C, and CA. And the three radical axes have to intersect at one point. So let's call this point O. Then by the definition of the radical center, you have OA squared equals OB squared equals OC squared. And this is because since it's a circle of radius 0, technically OA is tangent to the circle at A, and similarly for B and C. And this basically simplifies into OA equals OB equals OC. So this shows that the circumcenter of a triangle does exist. Okay, so now we'll be looking at example 2. Okay, so you have a triangle ABC. And the circle of ABC is gamma. And we have a point D on BC, and the tangent to this circumcircle at A okay, so the tangent to the circle at A intersects the line parallel to BA through D at a point which we'll call E. And then we have that CE intersects the circle at F, and BDFE is cyclic. So we want to prove that AC, BF, and DE are concurrent. So kind of like the orthocenter example, there are 3 lines that we want to prove are concurrent. So this kind of makes us think of finding 3 circles whose radical axes are these 3 lines, so that we can show that they do all go through one point. Okay, so I'll draw in the circumcircle of BDFE. Okay, so one thing that we can that we'll notice is that the radical axis of the circle through B, D, F, and E and gamma is BF. So this makes us want to look for a circle that goes through A, C, and DE. So basically, we want to prove that ADCE is cyclic. And we can do this through angle chasing. And yeah, so basically we have that angle EAC is congruent to angle ABC. Since the circumcircle of ABC is tangent to AE, and since AB and ED are parallel, angle ABC is equal to angle EDC. And this basically gives us what we want since EAC is equal to EDC. So now that we've showed that ADCE is cyclic, we can see that okay, so we can see that the radical axis of this circle and gamma is AC, and the radical axis of this circle and the circle through BDFE is DE. So by the radical center theorem, these three lines are concurrent. Even though they don't really look concurrent, but yeah. So in general, if you have three lines that you want to prove that are concurrent, or they're all parallel to each other, and there are circles in the diagram, looking for other circles and radical axes can be very useful. Okay, so now we can do one of the exercises. Okay, we can do problem 3.2. So you have an acute triangle ABC where angle B is greater than angle C. And the midpoint of BC is M, and the feet of the altitude from B and C are E and F respectively. And we let K and L be the midpoints of ME and MF. And we let T be a point on the line KL such that TA and BC are parallel. So we want to prove that TA and TM are equal. Okay, so the first step is labeling the orthocenter. And the reason this is useful is because we can see that AFHE is cyclic, since AFH and AEH are both 90 degrees. And the reason that this is special is because TA is tangent to this circle, and the reason this is true is because the center of the circle is the midpoint of AH. And since AH is perpendicular to BC and BC and TA are parallel, AH and TA are also perpendicular. So the center of this circle, the segment connecting the center of the circle and A and TA are perpendicular. Okay, so now you can see that the power of point T with respect to the circumcircle of AFHE is equal to TA squared. And we want to show that this is equal to TM squared. So this basically, again, comes back to the idea of having circles of radius 0. So we want to somehow use the fact that L and K are midpoints of M, E, and MF. So yeah, okay, so if you let the midpoint of AH be O, then we basically you can see that OF and OE are equal since they're both radii. And we want to show that OFME is cyclic, because if this was true, then OFM and OEM will both be 90 degrees, which implies that MF equals FM and EM are both tangent to the circle. And from this, you can see that LF squared is equal to LM squared, since L is the midpoint of MF. And constructing a circle of radius 0 at M shows that basically the line through L and K is the radical axis of the circumcircle of A, F, H, E, and M. Okay, so basically we can see that BFEC is cyclic, since BFC and BEC are both 90 degrees. And since M is the midpoint of BC, MB equals MF, which is equal to ME, which is equal to MC. And this basically shows that OFM and OEM are congruent. So from this, we get that, sorry, MF is, so basically just going back to what I said before, but working forward this time, we have MF and ME are tangent. To the circumcircle of AFHE. So, and we also know that LF, so LF squared is equal to LM squared, and KE squared is equal to KM squared. So LK is the radical axis of the circumcircle of AFHE and the circle at M. And since by definition T lies on LK, we know that TA squared equals TM squared, which means that TA equals TM. And this is basically what we wanted. So we're done. And I think we're out of time, so that's basically all I have. Thank you for listening.